So in this video I'm going to go through the exam questions at the end of 17.1, which are all based on mass spec. And the first question here is multiple choice, and they want to know which of the following alcohols is likely to have a fragment ion with a mass charge ratio of 31. To do this, you might have to use a little bit of trial and error. So the only atoms I've got in each of these alcohols are carbons, hydrogens and oxygens, and I need to work out a fragment that's going to have a mass of exactly 31. So I started off here by maybe trying to include 2 carbons. Okay, so if I had 2 carbons in my fragment, each with a mass of 12, I would have a total mass of 24 for my 2 carbons. In order to bring that up to 31, I would then need to include 7 hydrogens. But C2H7 does not exist. Okay, if I have 2 carbons, I can only fit 6 hydrogens around them. Because C2H7 does not exist, then that cannot be my fragment. Okay, then I tried having 2 carbons, again giving me a mass of 24 and including an oxygen, so that O there represents oxygen, it's not a 0. Oxygen has a mass of 16, so if I have 2 carbons and an oxygen in my fragment, even before I've added any hydrogens, it's already, the mass is already too great. So then I tried, what if I just used 1 carbon? Okay, that's got a mass of 12, and I used oxygen with a mass of 16. A carbon and oxygen combined gives me a mass of 28. I need to bring that up to 31, so I could include 3 hydrogens to bring me up to 31. In terms of drawing that out, if I've got a carbon bonded to an oxygen, can I fit 3 hydrogens? Yes, I can put 1 hydrogen on the oxygen, and I can put 2 hydrogens on the carbon. So I'm looking for a CH2OH fragment on one of these alcohols. So if I go down through them and see where I have an OH bonded to a CH2, here my OH is bonded to a CH, here my OH is bonded to a C, here my OH is bonded to a CH, here my OH is bonded to a CH2, meaning my answer is going to be D. Okay, if I lose that fragment there from that molecule D, it will have a mass of 31. The next question is also multiple choice, and it wants to know which alcohol is not likely to have a fragment at mass charge 43. So 43 is one of those common ones, and it is typically from a C3H7. You can draw C3H7 in 2 different ways. It can be a CH3, CH2, CH2, or you can have a CH3 bonded to a CH that's bonded to another CH3. The other common fragment with a mass of 43 is a CH3 bonded to a C double bond O. So I need to look through these alcohols and see if these fragments are present. So it's really easy to see on B that you've got a CH3, a CH2, a CH2. So I know if I were to break molecule B right there, then the first fragment would have a mass charge of 43. Same in C, again I can see I've got my CH2, I've got my CH2, I've got my CH3. If I were to break the molecule right there, I would get a fragment with a mass of 43. D is slightly harder to see, so I've drawn it out for you, okay? But you've got 2 CH3s on a CH, and if I were to break this fragment right here, I'd have 1, 2, 3 carbons, 7 hydrogens. That fragment would have a mass charge ratio of 43. Okay. However, A, if you look at A, even though yes, you've got 3 carbons bonded together there, that final carbon only has 1 hydrogen on it. I'm not going to get my mass charge ratio of 43, and there's no carbon double bond oxygen, so this other option doesn't even come into it. So your answer there is going to be A. That's the one that is not going to give you that fragment. Another multiple choice question, this time on an ester. Which statement is most likely to be true? So the first peak they give you is at 45, and they say it's due to this fragment. So the first thing I would do is just add up the formula, or calculate the formula mass of the fragment and make sure it's equal to the mass they've given you. So when I do that, it is, okay, so this fragment does have a mass of 45. Once I've confirmed that, I need to look at the molecule and see if it's possible to get this fragment. Do I have 2 carbons, 5 hydrogens and an oxygen all together? And I do, okay, if I were to break that bond right there, I would have C2H5O with a mass of 45, so A is likely to be true, okay? So straight away I'm thinking A is most likely my answer, but I'm going to go through the others and make sure that they're wrong. So the next one, it says that the peak at MZ44 is due to this fragment. So again, I confirmed that that fragment does have a mass of 44, but now I go and look at my molecule to see if I've got 3 carbons and 8 hydrogens anywhere, and I don't, okay? I don't have 3 carbons in a row, so that fragment does not exist from this molecule. The peak at MZ88 is the M+1 peak, okay? To work this out, I calculated the formula mass of the entire molecule, and I found that it was 88. Okay, so you are going to see it a peak at 88, but it's not the M+1 peak, it's going to be the M+ peak. The peak at 88 is the molecular ion peak. The M+1 peak would be at 89, so the mass of the molecular ion plus 1. Remember, those M+1 peaks are because of a small amount of carbon-13 that would be present. So C is also incorrect. And the last one, there is no peak at MZ is 43. So we've just had this number 43 above. We said that 43 is typically caused by C3H7 or a CH3 directly bonded to a carbonyl group. And if I scroll down here, I can see that I have a C double bond O directly bonded to a methyl group. And that would give me this fragment here would have a mass of 43. So I would have a peak of 43. Sorry. So that should be an X. There is a peak at 43. Therefore, as I originally thought, my answer is going to be A. So the next question, they give you a mass spec and they ask you which ion is responsible for the peak with the greatest relative intensity. So you've got relative intensity here on the y-axis. The highest peak on the y-axis is this peak here, which is at 43. So you need to see which of these ions is responsible for the peak at 43. So again, we've seen 43 quite a few times now. It is typically C3H7, which can be written out in 2 ways, or it's a CH3 C double bond O. And if you look at your possible answers, you can see that you've got 2 answers that do fit the mass. So I've got a CH3 times 2 bonded to a CH, which is what I have got here, C3H7, that has a mass of 43. And I've also got a CH3CO, which would have a mass of 43. But if you look at the actual molecule they're asking you for, and I've drawn it out here, you will see that there is no carbon double bond oxygen in the molecule that you've been given. However, you do have a CH bonded to 2 CH3s. So that fragment there will give you the right mass. So it will give you a mass of 43, and it's also present in the molecule. So your answer for this one is going to be C. Okay, so in this next question, we move away from multiple choice. The first question asks you to confirm that the molecular formula of this alkene is C6H12. You need to do this using the empirical formula that you're given and using the mass spectrum. So in order to calculate molecular formula, when you're given empirical formula, the first thing you do is find the formula mass of the empirical formula. So I've got 1 carbon, 2 hydrogens. The formula mass of CH2 is 14. I then need to use my mass spectrum to find out what the formula mass of the whole molecule is. And to do this, I go to my mass spec and I go to the highest peak. Okay, and there's here at 84, that's my M+ peak. Yes, you've got a tiny little peak here at 85, and that'll be your M+1 peak. This is your molecular ion peak. So that tells me that the mass of the whole molecule is 84. So I take the mass of the whole molecule, 84, I divide by the relative formula mass of the empirical formula, 14, and I end up with the answer of 6. I then take my empirical formula, CH2, multiply by 6, and I confirm that the molecular formula is indeed C6H12. Now on the mark scheme, it says that most students took the molecular formula, they took the 84 from the mass spec, and they just showed that the formula mass of the molecular formula added to 84. That will not get you the mark, because doing it that way, you're not using your empirical formula, and you have to use your empirical formula. So this is the only method that's going to get you 1 mark. The next question, it asks you, it says that the analysis showed that the alkene was hex-2-ene, and they want you to suggest possible structures for the peak here, peak 1, which has a mass charge ratio of 41, and peak 2, which has a mass charge ratio of 69. So the first thing I did for myself was just draw hex-2-ene, always draw it out, and I'm just drawing it out here. There is my hex-2-ene. And now I'm going to start looking at the peaks. So the first one I looked at was actually the 69. That number by itself doesn't mean anything to me in terms of what might be involved. So what I did instead was let's try and figure out what hex-2-ene has lost to give me a mass of 69. So I took the 84, the mass of the whole molecule, I minus 69, and I saw that if they had a fragment of 69, they must have lost a mass of 15. Now 15 does mean something to me. It's typically a CH3. So if I come down here and look at my hex-2-ene, if I just remove a CH3, then what I'm left with, that fragment, has a mass of 69. So I could remove the CH3 from this end, or I could remove the CH3 from this end. It doesn't matter. So I'm talking about the second peak, so I'm going to make sure I write it in the correct box. I'm going to remove it from that end, and that means my peak is going to be CH3 bonded to a CH, double bonded to a CH, bonded to a CH2, bonded to a CH2, and because it's a fragment responsible for a peak, it must be an ion, so I include my positive charge. It doesn't matter where I put that charge, but you need to include a positive charge. Okay, and that's peak 2, the peak that is at 69. I've just lost a methyl group, giving me a fragment with 69. The next peak, again, or peak 1, is at 41. Again, that's not a number that really meant much to me. So I took the total mass, 84, subtracted the 41, and saw that in order to have that fragment, I must be losing something with a mass of 43. And again, 43 is a mass that means something to me. It's typically C3H7, so a CH3 bonded to a CH2 bonded to a CH2. And if I look at my molecule here, I can see that that is a possibility. If I were to break my hex-2-ene right there and lose the CH2, CH2, CH3, this part of my molecule would have a mass of 43. The remaining part of my molecule would have a mass of 41. So it must be this part of the molecule here that is responsible for my peak. So I'm going to draw in that part of the molecule, CH3, CH, double bond to a CH. And again, because it's producing a peak, I need to include a positive charge. So there's 3 marks going for this. You get 1 mark for each of the structures, and you get your 3rd mark for remembering to include the positive charge on each. It doesn't matter how you draw your structures. You can use displayed, you can use structural, you can use skeletal. You cannot just use molecular. So for example, if you just wrote here C3H5, okay, you're going to lose a mark, okay, because you haven't really shown what part of the hex-2-ene is responsible for the fragment. Similarly over here, if you just lumped all the carbons and hydrogens together as a molecular formula, you're going to lose a mark. So next we move on to question 6, which is probably a little bit trickier. They tell you that this is the mass spec of an alcohol, and they want you to determine the structure, and they don't give you any other information. So the first thing I'm going to do here is I'm going to look at my molecular ion peak, because this tells me the molecular mass of my alcohol. So I go here to the highest peak, it's at 60, so my molecular ion peak is at 60. This is actually really important information. You can do a lot with this, okay? You know it's an alcohol, so you know it has to have an OH group. If it's got an OH, the formula mass of that OH is 17. So 16 for the oxygen, 1 for the hydrogen, formula mass is 17. Okay? You know also in an alcohol that you're going to have carbons and you're going to have hydrogens. So I take my 60, the total mass of the alcohol, I minus the 17, the formula mass of the OH group, and I'm left with a mass of 43. So if I'm left with a mass of 43, well, how many carbons and hydrogens can I fit in? Well, we should be familiar with that number 43 by this stage. 43 represents 3 carbons and 7 hydrogens. So by using my molecular mass, I've worked out my molecular formula. I know I have to have an OH because it's an alcohol, and that leaves me room for only 3 carbons and 7 hydrogens. So there's my molecular formula, C3H7. Once I know my molecular formula, I can draw out the possible structures. So if I've got 3 carbons, I can put all 3 of them there in a chain, and I can put the OH group at the end to give me propane 1-ol, or I can have my 3 carbons in the chain, the OH group in the middle to give me propane 2-ol. So these are both alcohols, they both fit the molecular formula. The last step then is to identify, well, which one of these is correct. And to do that, you're going to need to analyse the fragment ion X. The ion X here has a mass charge ratio of 31. And we actually came across this number in question 1 today. And we saw that it was a CH2 and an OH that was responsible for this fragment here at 31, and we went through a process of how we figured that out. So if you want to go back and look at question 1 again, you can, okay? So this is the fragment that is responsible for this peak at 31, and I'm making sure to include my positive charge there because only ions produce peaks. So if I know that I have to have an OH bonded to a CH2, then I can use that information to decide between my 2 different alcohols. In propan-1-ol, I do have an OH bonded to a CH2. So if I were to break propan-1-ol right here, I would get this fragment with a mass charge ratio of 31, which I see on my spectrum. On the other hand, over here, the OH in propan-2-ol is bonded to a CH group, not a CH2. Therefore, there is no way I'm going to get that fragment at 31 from propan-2-ol. Therefore, my answer must be propan-1-ol. Now, in terms of laying out your answer to make sure you get the marks, okay, you get a mark for identifying that the molecular ion has a mass of 60. So if you just label that on your spectrum like I've done, that's fine, it gets you the marks, or you can write it in words. But your first mark is just going for identifying that the molecular mass is 60. Your second mark is going for presenting the 2 possible structures. So you use your mass to work out your molecular formula, but then you need to actually draw out 2 structures. And you can use skeletal, or you can use structural, or you can use displayed, but you do need to show the 2 different structures. Just showing the molecular formula by itself is not enough, so you get your second mark for that. And then you get your third mark for analysing your peak, your ion X. So I've written it here just again on the spectrum, that's fine, I get the mark for that, but you have got to show the positive charge on that ion in order to pick up the mark, and then you have to link that back to your structure. So really here I should write a sentence, and I should say that it must be propan-1-ol, or I can just draw propan-1-ol as it has the CH2OH plus fragment. So just something linking that fragment back to propan-1-ol in order to get your third mark. Okay, so number 7, last question. You are again given a mass spec. You are told it's an alkane and you are asked to analyse it. So again, the first place I'm going to start is the molecular ion peak. If you look at the molecular ion peak, it's at 58. That tells me the formula mass of this alkane is 58. I know it's an alkane, therefore it only contains carbons and hydrogens. I just need to figure out how many carbons it contains. So with a formula mass of 58, the maximum number of carbons it can have is 4. Okay, if it had 5 carbons, that would be a formula mass of 60 before you even consider the hydrogen. So the max I can have in there is 4. 4 12s are 48. That gives me a mass of 10 for the hydrogens. That gives me C4H10, which fits the general formula of an alkane. So I know I've got C4H10. Your first instinct straight away might be butane, okay, but there is more than one possibility for an alkane with the molecular formula C4H10. Yes, you can draw it straight chain like butane, but you could also draw 2-methyl propane, and that would still fit the bill of C4H10 and being an alkane. So in order to deduce which one is correct, you need to analyse the other 2 peaks. So you've got peak 1, we said was C4H10, the molecular ion peak. Peak 2 has a mass charge ratio of 43, a number that we've seen before. It's the C3H7. And then peak 3 has a mass charge ratio of 29, which means that it's the C2H5. So when you are identifying the ions responsible for these peaks, make sure you include your positive charges, okay? You're not going to get the marks without your positive charges, okay? So now that we know what those peaks are, if we look at our 2 possible structures, we need to see which fragments are possible for each. So if I've got butane, I can get an unfragmented butane, which would give me a peak at 58. So I could get peak 1 from butane. I could also get peak 2 C3H7. If I were to break butane just here, I would have C3H7. So it's feasible that I would get peak 2 from butane. And then the last one, peak 3, if I were to break it here instead, I would get 2 C2H5 fragments. So all 3 fragments I can get from butane. However, when I look at 2-methyl propane, I can only get peaks 1 and 2. So I can get the unfragmented ion giving me a mass of 58. I can get peak 2, okay? If I were to break off this CH3 group here, I'd have a CH3 bonded to a CH, bonded to a CH3, giving me C3H7 in total. But I cannot get peak 3, okay? There's no bond that I can break that's going to give me a C2H5 fragment. And you can try if you want, but you will not get a C2H5 fragment by breaking a bond. Therefore, 2-methylpropane cannot produce peak 3, therefore the alkane in question is going to be butane. So in terms of your marks here, it's for 5 marks in total. You get 3 marks for just identifying each of your peaks. You have to include the positive charge, okay? It's fine to write them in molecular formula in this case as you're figuring things out, but you need to include your positive charge. Then you need to show the 2 possible structures, and then you need to use the information from your peak analysis to identify which structure is correct.